here to talk to you about things I'm sure we both share in common, which is the joy of programming, and I'm going to talk about joy of functional programming. But before I get started, one of the traditions that I have giving keynotes here is to invite somebody here on stage. But I'm going to put a little rule, a little restriction today in doing so. So I want everybody to stand up for a minute, just for a second, if you would please. Yourself first, please. And I want the men to sit down, only the men to sit down. To volunteer to come up here on stage with me so we can co-present this. Who's going to be here for me? Come on. Who's going to come up here? Don't be shy. Come on over. And he's going to give you a microphone as you walk down, and then we'll get started. Well, while she's making her way up here, I want to talk about a few things. Oh, I apologize. The remaining ladies, please sit down. So I want to talk a little bit about what I'm going to talk about here today, just to give you an expectation. I'm going to spend maybe about 15 to 20 minutes not talking about programming at all. So I want you to be aware of it. If you're eager to talk about programming, that's not going to happen for about 20 minutes. I'm just going to set your expectation. So if you're going to say, what is this guy talking about? I want you to be aware, I'm not going to talk about programming for quite a while. I'm going to wait for her to show up over there. She can get the microphone, walk up here. And then I'll talk about programming after that, and then we'll get to some fun stuff that we can talk about. So I've got about 55 minutes or so on my hand. That's a pretty good time. We'll do that. So, all right. So we all work in organizations. And what is the reason why you're here today? And I'll tell you one reason why you're today. I can guarantee you that. You're not here today so you can go back on Monday and do the same old stuff. If that's what you're going to do, why do you bother being here, right? So you want to learn new things. You want to take back some ideas and you want to apply. And those new ideas you're going to pick up from people who are speaking. You're going to pick up from people around you who are attending conferences. You're going to be interacting, and you're going to pick it up from thoughts that emerge in your brain. It's like, wait a minute, I was not thinking about it that way, right? And come on over.
Hi, sir.
What's your name?
Antriksh.
Antriksh. Pleasure to see you, Venkat. And what do you do?
I'm Java programmer.
Excellent.
Working in Accenture.
Awesome.
And my experience is for like 6 years.
All right, let's move over here. Excellent. Good to hear that. So I'm going to just interact. Yeah, please go. A round of hands. Yes. Absolutely.
Hi.
Are you nervous?
Not really.
Excellent, because at least one of us is not nervous, right? I am nervous every time I give a talk, so absolutely, that's great. Well, so here's the deal. We're just going to interact, talk about stuff. So, well, somebody comes to you, and they're talking about, solving a problem, and then you say, well, wait a minute, you could actually use this other language or other technique, and you could solve this problem.
Okay.
What is the first thing they normally tell you when you say that? Something that they're not familiar with, and you suggest this, and what do they tell you?
I mean, what I'll think about
what they respond. Let's say I'm the guy who's solving this problem,
okay.
And then you say, oh, why don't you use this XYZ? Okay. I'm like, XYZ, I've never heard of it.
Yeah.
And what am I going to say? How am I going to react to it? Normally, what do you see people do?
He'll say, are you crazy?
Yeah, thank you. Right? Are you crazy, right? People are that polite to you, right? They say more or worse things to me, right?
Yes, inside.
Yeah. So one of the things that people often ask is, and I've been asked this several times, who's using it? Are people really using this? How many companies are using it? Are big companies using it? Have you ever heard this? Yes. I want you to think of this word. Mainstream. How many times have you been asked, is everybody doing it? If nobody is doing it, if big companies are not doing it, are you crazy to tell me to do it, right?
That's right.
That's kind of what they're asking you, right? So you're right on, and we both are feeling the same pain when we suggest things, right? I want you to think about this word mainstream. I want you to keep thinking about this term mainstream, because this is what I face every day. When I go to companies, when I go to teams and I suggest things, the very immediate thing is, Who's using it? There's a lot of people using it. Is it mainstream? So let's talk about mainstream for a little bit, right? And I promised I won't talk about programming for a while. So let's talk about mainstream. So I want to start out by saying we are doing it wrong. Do you think so? Are you married?
Yes.
So you have said to your husband several times, you're doing it wrong.
Yes.
Yeah, I know it. I've got a lovely wife who keeps me on the floor, reminds me every morning, Venkat, you're doing it wrong.
Yes.
And my wife, actually, I have two boys.
Okay.
Wonderful boys, 15 and 11. But my wife says she has 3 boys.
That's right.
Yeah.
I have adopted one boy.
Moms are very clever, right? They try to grow up the kid and then they push them away as soon as they can.
That's right.
Absolutely. Well, they say it takes 40 years for a person to grow up. They haven't known me, right? That hasn't happened. Anyways, we are wrong. In fact, we are so wrong in so many times, in so many levels. Unbelievable in the ways we are wrong. Let's talk about that for a second. I'm going to take this ball here, right there. See ball there in the screen? I'm going to drop that ball. What's going to happen when I drop that ball?
I'm positive, so I'm going to catch it.
You're going to catch it. Awesome. Well, it's only you're not going to be able to catch it. What's going to happen to the ball?
It will drop.
It will drop and bounce away. Yes,
Yeah.
it just did, right?
Yes.
It just did. But why? Why did it do that?
It doesn't bounce back.
Yeah, but why did it even fall? Why didn't it just go up?
Gravitational.
Gravitational force. Man, and how do you know that?
Einstein.
Einstein? Actually, it's Newton.
I'm sorry.
That's okay.
It's okay. Newton.
Newton was the Einstein of his time. Absolutely.
Thank you to save me.
But you're wrong. And guess who else was wrong? I was wrong too. Because I just said Newton, and everybody said, of course, right? And they all said, of course it's Newton. And guess what? Everybody here is wrong in so many levels. Because there's one smart, cool dude a very long time ago. You know what his name was? Aristotle. And Aristotle kind of had this little feeling. He said, you know what? Stuff falls, isn't it? See, when things fall, what do? Stupid thing, it falls, we walk away. Not this guy. He's like, why does it fall? He got it wrong too. And it's perfectly okay to get things wrong. Even Aristotle got it wrong. And he called it gravitas. The meaning is heavy. He said it falls because it's heavy. We know it's not true anymore. But that's what he thought. But he was wrong. It's okay to be wrong. And then he came up with this. Well, guess who did after this? A guy very close to where you and I are standing. His name is Bhaskara. And he was actually from Karnataka. And he's the guy who actually coined the term gravity. This was back in 11th century. And it took about, 10 centuries before somebody could come back and say, I got a little bit more clue about this. Well, then came along Copernicus. Then came along Galileo. You see, Newton was not even in the picture right now, right? And then came along, of course, Kepler. And then came along Robert Hooke. And eventually, of course, we all talk about Newton and his apple, which really never happened the way they tell us that it is, right? But the point really is, Newton really kind of formulated a lot of ideas that a lot of other people have done before him. But really what Newton did was not about gravity as much, actually. His real work was to really talk about this inverse square law, where he actually talked about how objects pull each other, and his main contribution was to say it's not just the apple, hey, but things far away, like moon gets pulled by Earth, which really is astronomical. Well, of course, he was an astronomer for that reason, mathematician, right? So again, notice how we are wrong. And it's okay to be wrong, but we got to know that we could be wrong, right? But a lot of us have this assertion that we are, of course, right. But we take time to learn. We took several centuries, actually, to learn along the way, and that happens quite a bit. What's the center of, our world? Not meaning to put you on the spot. What's the center of our world? I heard somebody say sun.
Universe?
No, well, universe is infinite. I don't even know if there is a center for
Okay.
it. I'm not that smart. But just our world, the world we live in, what's the center of that? The sun, right?
Yeah.
Well, but we didn't know that. We really don't know that. Why? In fact, for a good 1,500 years, it was believed that Earth is the center of the celestial world we know of. In fact, it was so much believed that the Catholic priest believed in this. And the Roman Catholic Church said, Earth is the center. You better not dare to tell them otherwise. That was the center of the earth, of the world. Well, then came along one small problem. People started sailing. They started going out in the ocean. And they were like a little puzzled. Okay, this doesn't match with this, right? The empirical observation doesn't match with your theory. Something is kind of wrong here. I'm not sure what's wrong, but that doesn't seem to go well with your theory, right? And so people started slowly, quietly, because it was not easy to talk in public those days, because you could get killed for doing that.
That's right.
Not very different from today, right? Yeah. And so they were thinking about this, and Copernicus is the guy who came back and said, wait, this is really wrong. Sun is in the center and not Earth. But did you notice one thing that Copernicus actually did? He was a smart guy, but look at what he drew. He drew circles. And he quite didn't get the idea that it may not be a circle. So he kind of changed radically a few things, but kept other things the same. And came along after a little while, this guy called Kepler, and said, no, it's not a circle, it's actually an ellipse. And what do people do to all these things? They said, you guys cannot be correct. The Roman Catholic Church knows what they're talking about. Well, eventually this guy who just couldn't keep quiet decided to say, maybe that's not true. So it turns out, Sun being the center of the universe, of the celestial bodies, were not mainstream. So the mainstream was actually completely different. Not what is mainstream today, right? Something different completely. And came along this guy called Galileo. What did he do? He created telescopes, started looking through the skies, and he had real evidence because he could see, just not talk about it. And he said, guys, you're wrong. In fact, this guy, Kepler, actually is right. And I'm going to promote Kepler's ideas. So Galileo was an observer, and he observed what was going on really to telescopes, and started saying, this guy Kepler is right, you guys are wrong. And guess what they did to him? They put him in house arrest. They put him in house arrest in 1933, and he was in house arrest for the rest of his life. And why? Because he did not agree with the mainstream. And he believed something which was radically different that Kepler had pointed out. Let's talk about health and childbirth for a minute. Now, take an example, right? A lady comes to you and says, you know what, I'm going to give birth to a child. I'm wondering if I should go to a hospital to have the baby delivered. Or I know this real nice old lady. She says she can come home and take care of me. I can deliver the baby. What would be your recommendation? Go to the doctor at the hospital or stay at home? This lady can help you.
In this era, it's hospital.
Absolutely, go to the hospital. And she very cleverly said that in this era, right? And now as we know it. Well, it turned out in 1800, you had 3 times more chance of dying in the hospital than if you had a midwife come and take care of you at home. Can you believe that? In 1800. And what do people say? Hey, that's mainstream, right? And people kind of went around, did their stuff, until this guy, who's an Hungarian, said, you know what? This is strange. People come to hospitals after surgery or childbirth, they die within a week. What's going on over here? 10 to 35% of mortality. Imagine more than 1/3 of the people die after childbirth or surgery. And he said, I don't know why. He didn't know. But he found something. He had a hunch. He had a hunch. And you know what he did? He did something remarkable. He washed his hands. He just washed his hands. And the minute he washed his hands and did surgeries, people didn't die as much. In fact, after he did these, the fatality rate was less than 1%. And you know what the doctors did? They said, really? You think you know better? You think this cures people? So what's causing it? He said, I don't know. I think there's something called germs. Really? Have you seen the germs? Can you show it to me? No, because they didn't have microscopes back then. And so they said, okay, you are speaking against authority, and they put him in an asylum. And 14 days after they put him in asylum, they bet him to death. And he actually died after proposing germ theory because that was not mainstream. And then came along, of course, other people. But he suggested something very simple. Wash your hands with soap, which is what we want to do today, right? You go to the bathroom, you go to the restroom, have a soap, wash your hands with soap. Before you sit down to eat, wash your hands with soap. And guess what happens? You don't carry germs with you as much. And you don't get sick as much. Number of sick days is very minimum if you do that, right? A simple matter of the fact was not a mainstream until 1860s. What an idea. Well, then came along Pasteur, and then came along Joseph Lister. These guys really took upon this idea and promoted the germ theory. Well, it turns out that washing the hands was not mainstream once upon a time. And it should be, right? We all can agree on it. Well, here is something else interesting. We hold these truths to be felt evident that all men are created equal. Where is that said? Anybody knows? I had to point to my American friends if they don't answer. Anybody answers, yes, Josh. Chinese Constitution. If it's got to be, right? Because nobody knows about it here. Any guess now? The Declaration of Independence. All men are created equal. I live in Colorado, and I travel quite a bit. I enjoy traveling. I enjoy seeing people, meeting people. And one of the things I did was I went to Mount Vernon. And Mount Vernon is really the palace or the cottage or whatever you want to call it of George Washington. Actually, the words you saw was written by Thomas Jefferson, a great buddy of George Washington, the first president of the United States. And I was going through George Washington's Mount Vernon, and I have to be honest about my feelings walking through that. As I was walking through it, on the wall it said, all men are created equal. And I looked through the window, and I saw the slave quarters. And I said to myself, how could this be true? Here is the guy who promoted equality of all men, and he's got a slave quarters right outside his door. And I felt confused. How could this be a great man if all he had is slaves? Is this real hypocrisy? How could this be true? And I said to myself, oh, wait, there is another problem here. You cannot change the world in one sitting. You want independence from the British? You get it. You cannot handle two wars at the same time. In fact, a war worse than winning the country from the British was winning people from slavery. And it took another 100 years for this nobleman to do that. And that broke a very, very, very intense civil war in the country. Several millions of people were affected by this. People died because people were fighting. People who owned properties called slaves. And how could you let go of that? Because, guess what? That's the way it was. Mainstream. It was okay to have slaves. Well, 1964, slavery is abolished, right? Everything is good, right? No, not really. Sitting next to a colored person was not mainstream. Oh no, you had your own bathrooms, your own restaurants, your own seats in the bus. It's not mainstream to sit next to a colored person. Absolutely not. And it took another 100 years for people like this, Rosa Parks. She was sitting in a bus, and she was sitting in a colored section, and all the places for the white people were filled up. And they said, you get up from there. We need to give a place for a white man. And she said, no, I won't. And guy next to her is Martin Luther King. It took another revolution for winning the equality. And did we achieve that? Not really. It takes time because those thoughts are not mainstream, right? Absolutely. And think of this, women's suffrage. This is a protest of women in 1913. What do they want? They want the right to vote. So we can have these clowns come to office, right? And can you believe it? Look at this number here. Because women having right like men was not mainstream. And guess what? I put that in the parentheses. Why? Because it is still not mainstream. Shame on us. And that's what the world we live in, right? It's not mainstream. And it turns out, 1893, New Zealand made it a law that women can vote. Look at these years. Unbelievable. 1985, Southern Australia. And about United States, my neighborhood state, Wyoming, in 1869, It took so many years, 1920, for the 19th Amendment in the US to say, yes, women can vote. And as I was reading through history, learning about it, all I can think of was this. Seriously? What the heck is wrong with these people? Are they born to women? Do they have daughters and sisters? How could somebody think like this, right? And again, that is not mainstream. So I want you to think about the word mainstream whenever you use that word. Because if everybody is doing it, it doesn't mean it's right. It probably is wrong. We don't know that. Could be. So I want you to assert the word mainstream. So don't go around asking people, what is everybody doing? Ask, what should you be doing? Because mainstream sucks. We got it wrong. We got it wrong so many times in history, right? What we're doing here today is not departed from history. We are part of the history. We're just in one profession doing it. But I showed you 3 other professions, maybe 4. I talked about healthcare. I talked about astronomy. I talked about, civil rights and voting rights. These are all parts of what we do as human beings, and programming is just another thing we do as human beings. And we reject good ideas. We do this all the time. And then we have a small minority of people saying, you know what? That sucks. That mainstream thing sucks. We should do this differently. And a new way of thinking is, but that takes time. And it's not mainstream. But this thing called bandwagon, we all get on this bandwagon. What is this bandwagon? We want to know what is mainstream. What is mainstream programming in the world? Can you tell me what's the mainstream programming paradigm today? What is everybody using today?
So like in Java.
Like in Java? What kind of paradigm, programming paradigm do we use? Object-oriented paradigm.
Oops.
Absolutely, yeah. Right? Object-oriented paradigm. We got on this bandwagon. But guess what? That is not true. That was not true once upon a time. It was procedural programming. Most people did that. Until this guy came. This is one of my favorite dudes. His name is Edgar Dijkstra. Edgar Dijkstra talked about dynamic philosophy problem, all those wonderful things about concurrency. But one of the things he's noted for is he wrote this wonderful article called "Go-Tos Are Evil." Don't use go-to in your code, he said. In fact, so much so, the 4-letter word go-to is a forbidden keyword in Java. You cannot use it. It's a reserved keyword that is bound not to be used. And that's what he wrote, and we kind of started exploring this thing called structural programming. And then that became mainstream for a while. And we were doing structural programming for a while. Then what happened? Well, these 2 guys, Dahl and Nygaard, 2 Norwegians, created this little interesting programming environment called Simula. And Simula was this wonderful programming language that introduced this concept called objects. They didn't quite name it that way. They said, look what we have here. We got some things that like a search structure, we can interact and pass messages. And they kind of created this thing called Simula. And then came along other languages along the time until one fine time there was this guy Bjorn Strustrup. And he was working on his PhD dissertation. And he was writing code. It ran really fast in a language predecessor to C, but it had so many bugs. It just wouldn't even run. He wrote it first in a language like Simula. It was easy to write, easy to maintain, but it was so slow, he was worried he would never graduate. And then so he wrote it in programming language like C, ran it really fast. It was so buggy. He graduated and then went to work for Bell Labs. They said, sit down here, think about what you want to do. He said, wouldn't it be so nice if I create a language that ran as fast as C, but gave me the power of object orientation? And a very gradual shift, like Washington's gradual shift. You can't change the world entirely in one day. And all was not mainstream back then. Not many people wanted to use it. There were a small group of small talkers sitting there and doing small talk, but not the rest of the world. And he created C++. And it caught like wildfire. However, this resulted in OO becoming mainstream. But what it really turned out to be is this. As this guy wants you to know. Who is this? This is Alan Kay. He is the guy who gave the term called object-oriented programming. And he said, I invented the term object-oriented programming. I can tell you I did not have C++ in my mind. And it kind of went on its own. This is like the Diwali rocket you fire, right? You have no clue which direction it's going to go, right? But it's fun to watch it still. And that's kind of what it does, right? Goes off in a tangent. But all of these tell us one thing. In the beginning, we think some ideas are really, really cool. Like this one that I saw on Twitter the other day. A school wanted to send a message to the children. And you know one message that we all try as parents, and I do this every day, I get an opportunity, I go to my children and say, you got to be good, you got to speak honesty, and you shouldn't do drugs. I say this to my children all the time. We're worried about as parents. So this company thought, what a great idea to send this message to the children not to do drugs. So they created this pencil. And the pencil said, too cool to do drugs. That's what it says. Too cool to do drugs. And they gave it out to children in schools. And it worked really well for about 2 weeks. And one 10-year-old kid suddenly found out something was happening. The kid was using the pencil, and the pencil kind of runs out. What does the kid do? Sharpen the pencil. And once the kid sharpened the pencil, it read, cool to do drugs. Then it says do drugs. Then it says drugs. Obviously, that message did not go very well. And they withdrew this pencil, right? So sometimes we have this eagerness, right? We have this like, hey, here's a great idea. Or this one. I heard the rumor that Coca-Cola wanted to increase their sale of their products in the Middle East. So they came with a campaign. They said, we'll show a guy in the sand, in the desert, fallen sick. He drinks a can of Coke and he's happy and running. And their sale just dropped. And nobody wanted to buy Coke anymore. And they found it eventually, these guys read from right to left. Right? So there was this healthy dude running, he drinks Coke. Oh my goodness, call the ambulance. Great ideas, isn't it? Uh-oh. So what happened? So what do you do every day? At work, that is. You write code as a programmer. You sit in Java programming, you write code, right?
Yes.
And so you write code. What do you do after writing code? Compile it. After compiling, what do? Come on, honestly.
I would really like to get it running.
She's got the same problem we do, right? I was hoping she had a different answer. I was like, can I come work with you? She's the same problem. You fix bugs, right?
Yes.
And after you fix bugs, what do? You write more code, don't you? Yeah. And what do? You fix more bugs now. Right? Come on, honestly. Yes? Absolutely. And then we write more code. And then we fix even more bugs. And then what do? Come back and write more code. What's this called? Somebody said, courage. Yeah? Programmers are the most courageous people, right? The compiler spits at you, yells at you, calls you by names. What do? You say, fine. And then you get back to coding, right? We're the most courageous people on hand. But that's not what I was asking for.
Never give up.
Yeah, never give up. That's correct. But what is this called? Mainstream. That's what we do, right? Everybody here agreed. That's what we do. It's got to be mainstream. But how does it feel to be in that mainstream? How do you feel being in that mainstream?
Very painful.
Not fun, isn't it?
Yeah,
not fun. And late in the night, you would rather be writing new code than fixing the stupid bug.
That's right.
Well, let's talk about functional programming. This was actually coined by, well, not quite functional programming, but this concept of Lambda Expressions. What an odd name, Lambda Expressions. Where does that come from? Well, this was by Alonzo Church. This guy was a mathematician, and guess what year this was created? Take a wild guess, anybody. What year? When did we start using object programming? 1989, 87, 88, whatever. When was this done? Anybody? Wild guess? 60s, 50s, 1929. 1929. Just like Aristotle and Bhaskara and various other people we talked about way long ago. These smart guys said, you know what, let's think about problem solving. And the problem they wanted to solve was computability. You know what, it's funny to think about this, right? We got devices on our hand today. We program at will. Affordability is cheap. You just get machines. Everybody has several devices with us. Back then, people didn't even know if machines can run programs. way back in time. This was like, hey, would machines actually run applications? Is it possible? Computability was unknown. And he was talking about one thing. Is there problems that are uncertain? They were uncertain about uncertainty. How cool that is. Right? And at that time, one of his students, Alan Turing, said, hey, I'm going to talk about a problem called the halting problem. What's a halting problem? They never knew whether it's possible to say whether an arbitrary program will ever halt. You know, it would have been easy today, because if they looked at my code, they would know it doesn't halt. Right? That's why I'm at work debugging, right? But back then, they didn't have code to run and see. They were kind of theorizing this. And they said, could we create an application that will prove whether any arbitrary program will ever halt? And he proved for the first time that it cannot be proven. And in turn, he emphasized this uncertainty theory. It was a very interesting time for computing, way back when computers, as we know it, were created. Then came on this really, really smart guy. His name is John McCarthy. And he created this wonderful programming language called Lisp. That's why I hear the whisper in the air. Lisp, it's okay. You're among friends. Say it loud. Right? He created Lisp. In fact, every language today is trying to really hard to re-implement Lisp. And he created Lisp. And he created Lisp using some of the very fundamentals in lambda calculus that these fine people created. And one of them that created was called pure function. What are pure functions? Well, let's understand what pure functions are. I need some exhibits here, and I found some. So how about this? Hold on to this. I'll give you some exercise here. Don't open it. Don't drink it. Okay. So this is pure function. Is the water good? Looks like it. Well, it's a pure function. Why? It's a pure function because, well, imagine you have a function where you call the function, it does something like a plus 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 b plus z plus 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 a plus plus. What do you think of that function? That's code from hell, isn't it? Too many variables changing with pluses, right? A pure function says, send me an input and I will send you an output. And while this function is running, it is not affected by anything outside. And it doesn't affect anything outside. That's a pure function. So a pure function says, if you give me one input, I will give you one output. If you keep giving me the same input over and over and over, what is it going to do? Same output over and over and over. Well, if that is true, guess what you're going to do? You call it once with an input, you get the result, and the next time you get the same input, what are you going to say? I don't have to call it anymore. I know the answer already. Make sense? Well, you just define what's called a referential transparency. So referential transparency says you can replace a function with its result after you computed it because the function is pure. It doesn't matter how many times you call this function, it's not going to give you a different result as long as the input is exactly the same. Make sense? And this gives us power for what? If you know that a function is pure, who gets the power of this knowledge? The compiler does. Because a compiler can optimize that code, right? So now I'm going to ask for your help. I want two functions with me. There you go. So here are two functions. And help me out here. Function A, function B. I don't really need to use one result versus another. They're independent functions. And I want to use the results of those two elsewhere down the chain. On the compiler, and tell me if I'm right or wrong, these two are pure. Okay. And I find that the register contains a certain set of data right now. Okay. And I figured, as a compiler, that this I'm going to run first because it's efficient, followed by that one. Is it okay for me to order them this way?
Yes, why not?
Absolutely, why not? She gives me the liberty as a compiler. I say, absolutely, great. But then, a little later I realized, you know what? Registers are a little different now. I'm going to do this. I'm going to run function 1 first, and then run function 2. Do you think that's okay?
Yes.
Absolutely, because they are pure, why not, she says, right? She, as a programmer, is happy with my optimization so far. Make sense? And I was able to do this, why? Because she was good in creating these two as pure functions. Or, as a Java compiler, there are two compilers, right? What are the two compilers? The Java C and the JET. As a JIT compiler, I come down and I realize, oh, look what I just found. I've got 2 cores in front of me. And I'm going to run one of them here, stay, and another one here at exactly the same time. Is it okay? Can I run them concurrently on 2 different cores?
Yeah.
Absolutely. And look at the optimization we're able to perform and all that we're able to do. Why? Because those 2 functions are pure functions.
Pure functions.
And one of the very fundamental bases in functional programming, wash your hands, be hygiene, keep purity, write pure functions. So you could write code in any language, but if you can wash your hands, maintain that hygiene, write pure functions, you're helping the compiler optimize your code really well, and the compiler can run these 2 sequentially, one after the other, or could run them concurrently on multi-core processors. It's entirely up to this, and that power comes from the purity of functions and referential transparency we talked about, right? So that is the first benefit we see in here. But the power of expression, we're able to express our ideas really well. Let's talk about Finding Nemo. Did you like that movie?
Yes.
It's an awesome movie. Kids like it, right? So why don't you come over and write some code here? Well, let's code. So I want to find Nemo. All right, so let's go ahead and let's see where we can write the code. I'm going to set my cursor over here. So here I'm in the main function. You're a Java programmer. You're kind of comfortable with this.
Yes.
So I'm going to create a list of string, and I'm going to say names equals arrays.asList, and I'm going to go ahead and give some character from Nemo, right? So right there is my character from Nemo. Some names, like you like Dory from Nemo?
Okay.
Not okay. You like Dory or you don't like Dory?
I like Marlin more.
Okay, all right. Well, the Dory is really special to me because I've got about as much memory as Dory does.
Okay.
Yeah. What's your name again?
Antariksh.
Antariksh. I asked you this a few times. Now you know why. I'm like Dory. I'll keep forgetting.
Okay.
Right? How are you doing, right? Okay. So we have these names here. And I'm going to output find Nemo, right? We want to find Nemo, right? That's what we're here for. Names. Antariksh.
Yeah.
Yes. Okay. So we're going to find Nemo. So let's go ahead and say public. And let's say static. Boolean, of course. And I'm going to say here find Nemo. And we got list of names, right? String names. And what should I do here? Antariksh, help me out here. I'm going to say Boolean flag equals false because we haven't found Nemo yet.
Yes.
It's a 3-hour movie, right?
Yes.
Okay, and then return flag, right? And then what do we do? For string name, right? Oops, I know how to type string. Name. Where does it come from? Names, of course, right? Names.
Yes.
And then I'm going to say if name dot equals, and who are we looking for?
Dory.
No, Nemo.
Okay, Nemo.
Okay. Well, she's clever. Man. Okay, Nemo. She's hard. Okay, so what do I do now? Flag equals true, and I'm going to break out of it. Do you think that code is going to work? Yes, no? Well, you're an experienced Java programmer. Your compiler ran in your brain.
Yes.
You parsed through it.
Yes.
That's like, yeah, absolutely, it's going to run. So let's run it. Oh, wait a minute. What's it complaining about? String, of course. Venkat spelling errors, right? String. Now, is it going to run? So you run it. True, we found Nemo. Excellent. What do you think of this code? It worked.
Pretty straight.
It's pretty straight.
Right.
Pretty straight. What? Let's change that word straight for a minute. What did she say? What's the word she used? Familiar. I understood what you're doing. It's familiar. It's mainstream. That's what she said, right? She just twisted the words, just like trying to trick me with Nemo and Dory, right? Yeah, it's mainstream, she said, right? That's mainstream. We took that imperative style of coding. That's what we did. What did we do? We did 2 things, didn't we? We told it what to do, and what were we trying to do?
Finding Nemo.
Finding Nemo. And we also told it how to do it. And how did we tell it how to do? Go set the flag called flag to Boolean false. Start one name at a time. Hey, Dory, is it you? And Dory says, what? Okay, never mind. And then we go through each one of them. We loop through each one of them. Did we do that? So we told it what to do, but also how to do it, right? It is low-level coding. It is primitive, but it's mainstream. Let's try this one more time. Again, you know how this Finding Nemo movie takes a turn when these cool Australian dudes come over?
Yes.
You know who I'm talking about? The turtles?
Yes.
That was awesome, isn't it?
Yes.
I love that movie, really. So that's how it's going to change now. So let's go take this code one more time. Let's comment out that nonsense we wrote, mainstream, and let's do this one more time. I'm going to simply say here, return, of course, names dot contains Nemo. Oh my goodness. The mole would have been over at the beginning. You want Nemo? Here he is. Keep him at home, right? There was no searching around the world, right? Which one would you code? Top one or the bottom one? Top one, of course. Because you're a consultant getting paid by the number of lines of code you write. Right? Otherwise the boss is like, what are you doing? I'm done. What do you mean done? Go back to the desk. We have billed the customers already. We need you to charge another week on this project. Okay, for I equal to 0. Right? What a nonsense. Right? We do this all the time. It's mainstream. It's familiar. It is straight.
That's right.
That's right. Absolutely, we do that, right? Absolutely. But we just used what has been in Java for a long time, which is the contains method, isn't it? Let's try this one more time. So let's get back to one other example. Let's move on from Nemo. We looked at declarative style. What did we do here? We tell it what to do and not
No, thank you.
how to do it.
Thank you.
Right? That's what we did. Is a number prime? A little bit more complex, right? A little bit more work. Is a number prime? Let's try this again. I want to know if a number is prime. How do I do that? Let's get back to the code right here. I want to know if a number is prime. We'll take a few examples as samples to work with. And we'll try this. So what am I going to do here? I'm going to go back to this code, and I'm going to say over here, is prime. So output is prime, and by definition, 1 is not prime. You know that, right? So 1 is not a prime. We know 2 is a prime. 3 is a prime. So I'm going to just put a few examples here, right? 3. 4 is not a prime. 5 is. So we're going to write this code. So what do we do? Public, again, static. And we're going to say Boolean one more time. Is prime, integer number. And what do I do here? I'm going to say if number is greater than 1. Otherwise what? Return false, right? That's my response right away. If it's not greater than 1, it's false. And then we're going to say Boolean flag. Okay, maybe not. For int I equal to 2, I less than number, semicolon. I less than number, right? And then I plus plus. And what should I do now? I'm going to say if number mod I is equal to 0, return true. Otherwise, return false rather. Otherwise, return true. Does that look familiar? Straight? Mainstream? Happy? It worked. What do you think of this code? We tell it what to do. We also tell it how to do it. We think we are the best people to tell how the looping has to be done. We sit there and say, I equal to 0. Have you gotten it? Yes. Go to the next value now. Go to the next value now. Right? We keep instructing the computer every step of the way. Why? Because the computer is dumb. It is, right? But doesn't mean we have to be at the level of the computer all the time, right? Well, it worked to get the result, but let's try this again one more time. But this time I'm going to go back to this code, and I'm going to say stream dot for a minute. And what do I want to do? Let's get rid of this garbage again for a second, can we? That all that code poof gone. Instead, I'm going to simply say return. Number is greater than 1, and what do? Int stream dot range for the value to number dot none match. And what is the match I'm looking for? Well, the number is not divisible by that index, and that's all I care to find out. And what did we just do? We told it what to do. Hey, what about the looping and all that stuff? Sit back, relax. We can do the looping for you. This is like me coming to the hotel, and Dilip arranged a wonderful hotel, but what shock they would have if I arrived with a big van. And they say, what's this van? Big 18-wheeler. It's got my bed in it. It's got my electric generator in it. Dude, where are you going? to stay over here. We got all of that for you. Just come with the stuff you need to come with. We'll provide you the infrastructure. It's a higher level of abstraction, isn't it? So notice what we did. We said in string range 2 to numbers. What is this? This is again a declarative coding style. We got exactly the same result for both of those. We even hear some music now, which means people are liking it. Right? How does it feel to write code like this? Imperative style is like working with a toddler. Do you have children?
No.
Not yet. You will soon realize this. A little kid, right? They're wonderful when they behave. But you got to tell them every step of the way. Sweetie, slowly get up, hold it with both hands, look where you're going, take small steps. Feels familiar? Right? That's how you talk to the children, right? Imperative style is like that. Every step you got to tell them, do this, do this, do this, do this. How does it feel to program in a declarative style, functional style? It feels like you're working with an adult. Well, okay, let me rephrase that. With a responsible adult, right? It feels that way, right? You say something and you get the results out of it, very convenient. Well, that's great. One of the things we did in both cases is this. We ceded control. We said, you know what? I'm not going to do all the work. I'm going to let you do it. What is that? How does it help? It helps by ceding control. It gives back control to the code. We're all used to external iterators, right? So if you have a bunch of numbers, what do you do with these numbers? You iterate one step at a time. So you say something along these lines, right? List integer, and then you say, for example, numbers. And then you would start saying, you know, whatever the value is for int I equal to 0, and then I less than. You are doing all the work. That's external iteration. In the case of internal iteration, what we do is we put it on autopilot. We say numbers, of course this is numbers, we say numbers dot for each do some work. This is called a higher order function. We're passing the function to a function. We did this a few times already. Now, what is the benefit of this turnaround? How does it feel? Well, what it feels like is, if you look at this code right here, we got to do all the work ourselves. It feels very low level. It's like having a dog that doesn't respond. You got to push it.
That's right.
This is like, she knows that, right? Dogs do that sometimes. This is like throwing a frisbee. How cool it is, right? The dog just leaps over, grabs the wrist. It's wonderful. Nice to play in the park like that. That's how it feels. It's on like autopilot, jumps over, runs over. It feels that way, right? That's the benefit. So it's a small change in syntax, but a huge change in semantic. How? How is the change? First change, tell, don't ask principle. Look at this code. You kept asking, how many elements do you have? Are you at the next element? Give me the next element. Do you have another one for me? Interactively asking over and over. What did we do here? Tell, excuse me, please do the looping. I'm done. Here's what I want you to do, right? We ceded control. And another big benefit, right? What is that? Polymorphism. Where is that coming from? Notice this code. That's totally non-polymorphic. What does it do? It iterates. How does it iterate? Sequentially. One step at a time. Hey, what does this do? Iterate. How does it iterate? I don't know. That's up to it to figure out. Is it sequential? Maybe. Is it concurrent? Possibly. I don't know. It's polymorphism, right? That's a benefit of polymorphism. I don't have to worry about it at this level. Benefit. So imperative style is opaque. It hides errors. Functional style is transparent. It reveals the details for you. Let's look at an example here. I want to find a stock price that is less than $500. I want to write an imperative code, first of all, for this, right? How would I write this? So I'm going to say list over here string. Well, actually, let's start with the values. So I'm going to say, string the symbol, let's say symbol, right? And I would say equal to empty. I want a stock price less than 500. So what do I do? For string, symbol, and where does this come from? Tickers.symbols, right? I'm starting with that. And I'm going to loop through. I'm going to get the price, first of all. So stock, util, right? And I go info. And I'll say stock info equals stock util. I've got all these classes behind me. So I'll say stock util dot get price for what stock? For the symbol that I want to give you, right? And I would say if the stock info dot price is less than 500, then I'm going to say symbol equals the stock info dot symbol, right? And I'm going to say break after this, get out of it. And then when I come out, I'm going to say, what is the symbol of this particular stock? I can find out and find the value, right? So let me go ahead and find out what the stock info is using. So info. And the stock info has a couple of things. It's got a ticker, not a symbol, that's why. So it's a ticker symbol I'm going to find out. So I'm going to say, go get me the ticker symbol for that particular symbol and give it to me, right? So where's the symbol here? So for string symbol in tickers.symbol, can you tell me where the error is? Oh, it's already defined, of course. Excellent. So now we got the value. Let's call it as result. Now you see the problems we face, right? These variables are called garbage variables. That's why it's interfering, right? We'll call it result. And then, of course, I want to set the result over here, and then I want to go back and define the result. So you notice how, because I defined it already, it's a garbage variable. It intervenes with what I'm doing. So what is the code doing now? It's going to the web, trying to find out what the stock price is. That is less than 500 in all the tickers I have. Hey, that was AMD. In the bottom, it displays it. I don't know if you're able to see it, right? It said AMD is the stock. I got a bunch of stock symbols to work with. What do you think of that code? Low level, isn't it? Let's redo this one more time. I'm going to keep this here around for a minute. Leave this here for a minute. I'm going to redo this. But how am I going to do this? I'm going to say here, output. And what am I going to output? Look at the way that I'm going to write the code now. Tickers.symbols dot stream, and I'm going to say in here, let's go ahead and say map stock util and get price. So I'm going to ask him to get the price. We're still using the same code we saw a minute ago. Filter, what do I want to filter? Only the prices. We'll say stock, and we will say give me the stock whose price is less than, is less than 500. Once you find them, find me the first, find first, and give me the result. So what did I do? I wrote a declarative code right here. But wait a second, let's go back to this code. Did that code work? Did the code work? The one in the top I commented out, did it work? Anybody see it work? Yes, it did. Is it correct? Notice that answers were fewer this time. A lot of people were quiet. Why? Because they're like, I'm not sure. In fact, if you write that code, something interesting is going to happen. About 3 weeks later, your tester, remember those testers? The tester walks in and says, hey, your code sucks. What do you say? You say, I know it. But tell me how it sucks today. I mean, that's what we don't know, right? We all know our code sucks. We don't know how it sucks today. And the tester says, well, I gave you a list with no symbols on it. Aha! Oh, of course. Duh. If you don't give me any symbols, what do? How do I handle it? It hides the details, right? Let's try this one more time. This code, I'm going to go run this and see what it tells us. It is still running, as you can see. We'll take a look at the result when it gives us. But it just doesn't give us the result. It gives more than the result. What is it going to tell me? Well, the result was AMD the last time, if you recollect, right? But this time it comes back, hopefully it comes back, and it is going to tell us that the price is still for AMD, but it's going to give us what is called an optional. Right there. It was waiting for me to say the word. Optional. Hey, wait a second. What's optional? See how revealing it was? It said, I'm sorry, it's possible I don't have an answer. You're like, oh, I better then get the value from it. You can specify or else or other functions to get it. So notice how revealing it was. So declarative code is revealing. It is transparent, right? But the imperative code, what did it do? It was lurking behind. I will hurt you when you don't expect the least. But this one is very revealing. So we found the stock price one more time. Now, I want a good code to read like a story, not like a puzzle. A good code reads like a story. Oh, nice, interesting. Oh, what a nice thing. It reads. A puzzle on there, like, wait, let me think about it. He is married to that girl over there who is brother of that killer. Wait. I'm getting confused here. Right? That's a puzzle, right? I want the story to be enjoyable. And I'm like, oh. And the code begins to read like the problem statement. What about efficiency, though? Oh, my God, look at what you just did. You went about writing this code in a roundabout manner, which means I'm going to go get all the tickers. How many symbols do you have anyways? Well, let's find out. Tickers.symbols, right? And notice I have, that many symbols, right? That's a lot. And what did I want? In fact, the result was just AMD after all, right? And I got all the values of the stock prices. And then I filtered every one of them. And then I gave you the first one. Are you crazy? Like you said in the beginning, right? You're going to loop so many times, isn't it? Well, let's find out. Let's go to stock util. And right in the top, I would simply say output getting price for what? Symbol, ticker. I save it. Go back here and run the code and see what it does. It's going to the web to find out. Well, if it went and found all the symbols and all the prices and came back, well, that's a lot of work, isn't it? If I had written the loop properly, I would have just gotten the first one, and I would have done a break, and wow, wonderful, isn't it? Well, that is another thing we have to keep in mind. We assume that code like this cannot be efficient. In fact, the evidence is the contrary in this case. How so? What's happening in this case is, you go to stream, and you say map. You know what it says? Okay. So here's the way to think about it, right? Here you go. You're not drinking it.
It's okay.
It's okay.
Yeah.
What did she do? She didn't use it right now. She said, I'll have it later. Make sense? Well, that's exactly what the map function did. It said, oh, you want to evaluate this? Thanks. I'll do it later. I'm done. You go to filter, and filter is his cousin. It's like, sure, done. And then you call find first, they're like, oh dear, let's get the work done now. So they're very lazy evaluation. So they don't really do the work right now, they postpone it, and as a result, what happens? Their efficiency is baked in, and it's got things stuck on the internet connection right there, but did it do extra work? It's lazy evaluation. And these functions are lazily evaluated, and I tweeted about this once. Efficiency is attained not by doing tasks better or faster, but by avoiding those that shouldn't be done in the first place. But the library is so efficient, it knows not to do some work it doesn't have to do. And as a result, we have lazy evaluation. And so the word lazy in functional programming is pronounced efficient. Let me hear you say the word lazy.
Lazy.
No, efficient. That's how it should hear, right? So efficient. So functional programming makes lazy evaluation and composition really easy. Hey, but what about speed? Well, let's go back to this code for a second, can we? I'm going to go back to this code that we wrote in the beginning. Remember? The one I kind of highlighted here and commented out? Let's say we wrote that code. Imagine that for a minute. And you have this code looping through. Look at the sequential code, right? And about 3 weeks goes by. One of your guys comes over and says, we got a problem. You say, what's the problem? The code is running very slow. How so? We got 200 stock symbols to evaluate. Oh my God, what do we do? And you're scratching your head, and one of your colleagues says, I got a bright idea job. That's called concurrency. That's not what we mean by concurrency. Quit the job, run away, because it's turned into a monster. How do we do this, right? So the point really is, we'll come back to this code. You say, oh, you want this to be running faster? Sure. But remember purity. This is pure functions. I change it to parallel stream. Now what happened? Just one small change. From the word stream to parallel stream. And the library says, sit back, relax, we do the looping. Now we will run the looping concurrently rather than sequentially. You don't have to do the extra work. You're the master. You sit there and flip the switch, and we'll do the rest for you. So you get concurrency almost for free. Why is that almost? You have to still flip the switch. Why? Because you know what you're doing, not me, the compiler, right? And that is the whole idea, is you can gain that kind of benefit. So mainstream, huh? So how do you deal with mainstream? So towering geniuses disdain a beaten path. And the beaten path today is imperative programming. It seeks regions hitherto unexplored for us to really change what we are doing. Imperative code is familiar. as we saw, declarative code is simpler. It can give us a lot of benefits. Concise, expressive, keeps our focus. No need to bring those garbage variables. The code begins to read like the problem statement. The code is transparent, not unique. It's easier to test because of its purity. As long as you give the same input, it gives you the same output. It's very easy to optimize and makes concurrency fairly easy. The biggest change in the programming world today is in the minds of the programmers. The compilers are done. The tools are ready. It's us who have to change. It's in our minds. So go enjoy the joy of programming. Thank you for your time.